Good morning. I am Aditi studying in BSc Chemistry Honors second year. Today in this video we are reading chapter Alcohol. Introduction. Alcohols may be regarded as hydroxy derivatives of aliphatic hydrocarbons depending upon whether the number of OH groups present in a molecule is 1, 2, 3 or many. Alcohol are further classified as monohydric, dihydric, trihydric or polyhydric respectively. It may be pointed out here that in dihydric, trihydric and polyhydric alcohols, each OH group is attached to a different carbon atom. This is because the presence of two or more hydroxyl group on the same carbon atom makes the molecule unstable and hence immediately loses a molecule of water to form an aldehyde ketone or a carboxylic acid. Monohydric alcohols. Alcohols containing one hydroxyl group per molecule are called monohydric alcohols. These can be divided into two broad categories: aliphatic alcohols and aromatic alcohols. Aliphatic alcohols. Alcohols in which the hydroxyl group is linked to an aliphatic carbon chain are called aliphatic alcohols. For example, methyl alcohol, ethyl alcohol, isopropyl alcohol. Aromatic alcohols. Alcohols in which the hydroxyl group is present in the side chain of an aromatic hydrocarbon are called aromatic alcohols. For example, phenyl methanol, 1 phenyl ethane 1-ol, 2 phenyl ethane 1-ol. Classification of monohydric alcohols. Monohydric alcohols are further classified as primary, secondary, tertiary according as the OH group is attached to primary, secondary and tertiary carbon atoms respectively. For example, primary alcohol, secondary alcohol and tertiary alcohol. Thus, it is evident from the above structures that the characteristic or functional groups of primary, secondary and tertiary alcohols are. Nomenclature of monohydric alcohols. Monohydric alcohols. The general formula of monohydric alcohols is CnH2n plus 1 OH, where n is equal to 1, 2, 3, etc. or ROH, where R is any alkyl group. These are named by the following three systems. Common system. In the common system, monohydric alcohols are called alkyl alcohols. Their names are derived by adding the word alcohol to the name of the alkyl group present in the molecule. For example, methyl alcohol, isopropyl alcohol, tertiary alcohol. Carbonyl system. In this system, methyl alcohol is called carbonyl while all other alcohols are named as derivatives of carbonyl. For example, methyl carbonyl, dimethyl carbonyl, trimethyl carbonyl, triphenyl carbonyl. IUPAC system. In this system, alcohols are alkanols. The name of an alcohol is derived by replacing the final E from the name of the corresponding alkane by the suffix -ol. The longest chain containing the OH group is selected as the parent chain and numbered in such a way that the carbon atom carrying the OH group gets the smallest number. The position of the substituents is then indicated by suitable numbers. The common and IUPAC names of a few monohydric alcohols are given below. Structure formulas, common name and IUPAC name. Methyl alcohol, methanol, ethyl alcohol, ethanol, N-propyl alcohol, propan-1-ol, isopropyl alcohol, propan-2-ol, N-butyl alcohol, butan-1-ol, sec-butyl alcohol, butan-2-ol, isobutyl alcohol, 2-methyl propan-1-ol, tersh-butyl alcohol, 2-methyl propan-1-2-ol. The IUPAC names of a few other substituted alcohols are given below. 4-methylhexane-2-ol, prop-2-ane-1-ol, 2,3-dichloro-3-methyl-butan-1-ol, but3-ene-2-ol. Methods of formation. Alcohols can be easily prepared by reduction of aldehydes, ketones, carboxylic acids, and their esters using a variety of reducing agents as discussed below. Reduction of aldehydes and ketones. Aldehydes can be reduced to 1 primary alcohols and ketones to secondary alcohols, either by catalytic hydrogenation, addition of H2 in presence of a catalyst such as Ne, PT, PD, Ru, or by the reduction with complex metal hydrides like sodium boron hydride and lithium aluminium hydride, abbreviated as LAH. LAH reacts violently with water, and therefore reductions with LAH are carried in anhydrous diethyl ether or tetrahydrofuran. In contrast, reductions can be carried in water or alcohol solution. Aldehyde, primary alcohol, ketone, secondary alcohol, propanol 1 propanol, butanol 1 butanol, cyclohexanol. Here the mechanism. Reduction of aldehydes and ketones by LiAIH4 or NaBH4 occurs by nucleophilic attack of hydride ion on the carbonyl group. All the 4 hydrogen atoms in LiAIH4 or NaBH4 may be successively used in reduction, and the alcohol is liberated from the intermediate metal alkoxides by the hydrolysis. Reduction of alpha beta unsaturated aldehydes or ketones. Neither LiAIH4 nor NaBH4 reduces isolated carbon-carbon double bonds. However, in case of alpha beta unsaturated aldehydes and ketones, LiAIH4 usually reduces only the carbonyl group, leaving the double bond intact. However, with NaBH4 the situation is somewhat different. Since aldehydes are more reactive than ketones, therefore in case of alpha beta unsaturated aldehydes the reduction of the aldehyde group occurs preferentially. For example, crotonaldehyde converted into crotyl alcohol. However, with ketones, a mixture of single reduction product and double reduction product is performed, in which the product of single reduction usually predominates. Since LiAIH4 has relatively stronger tendency for reduction at the carbonyl group, therefore, in the above case, it gives 98% of cyclohex 2-ene-1-ol and 2% of cyclohexanol. In contrast, hydrogenation of C double bond C is much easier than that of C double bond O. Therefore, reduction of CO cannot occur without reducing C double bonded. In other words, catalytic hydrogenation reduces both the double bond and the carbonyl group simultaneously. Crotonaldehyde and butyl alcohol. To prepare exclusively an unsaturated alcohol from an alpha beta unsaturated aldehyde ketone, a selective reagent such as NBBN is used. A selective reagent is that which attacks one of the several different functional groups. Because of the bulky organic group attached to boron, NBBN adds to C double bond O much more readily that it adds to C double bond thus. Mervian-Pondorf-Verley reduction. It is commonly used for the reduction of ketones to secondary alcohols. The reaction is usually carried out by heating a ketone with aluminium isopropoxide in presence of isopropyl alcohol. During the reaction, ketone is reduced to secondary alcohol at the expense of isopropyl alcohol, which it oxide to acetone. To push the equilibrium in the forward direction, acetone is distilled off as soon as it is formed. Ketone, isopropyl alcohol, secondary alcohol, acetone. This reaction is highly specific for aldehyde and ketones and does not reduce carbon-carbon double bonds. Therefore, it is a useful method of reduction of alpha-beta unsaturated aldehydes and ketones to alpha-beta unsaturated alcohols. Mechanism. This reduction occurs through hydride shift as shown below. Reduction of carboxylic acids. Carboxylic acids can be reduced to primary alcohols by LiAiH4. Carboxylic acid, primary alcohol, butyric acid, 1-butanol, benzoic acid, benzyl alcohol. Because of the excellent yields it gives, is widely used in the laboratory. Since it is somewhat expensive, therefore it can be used in industry only for the reduction of small amounts of valuable raw materials to be used in the synthesis of certain drugs and hormones. Mechanism. Like aldehydes and ketones, the reduction of carboxylic acids by LiAiH4 also occurs through nucleophilic attack by the hydride ion. The initial product of reduction is an alkoxide ion from which the alcohol is liberated by hydrolysis. Carboxylic acid, primary alcohol. Carboxylic acid can also be reduced to primary alcohols with diborane. Reduction of esters. Esters can be reduced to alcohols by the following methods. Butylant blank reduction. This method involves the reduction of esters to alcohols with sodium in refluxing alcohol. Actually, a mixture of two alcohols is obtained, one from the alkyl group and other from the alkoxy group. For example, alkyl part, alkoxy part. Ethyl butyrate and butyl alcohol. Ethyl alcohol mechanism. This reduction is believed to occur in several steps involving transfer of one electron at a time and the alcohol acting as the proton donor to the intermediate radical anion thus formed as shown below. Reduction with LiAiH4. Esters can be reduced with LiAiH4 to give a mixture of two alcohols, one from the alkyl part and the other from the alkoxy part, ester. Ethyl butyrate and butyl alcohol, ethyl alcohol. Mechanism. The reduction occurs through initial nucleophilic attack of the hydride ion on the carbonyl group with the expulsion of the alkoxide ion to yield the aldehyde intermediate, with upon subsequent reduction yield primary alcohol. Catalytic hydrogenation. On commercial scale, carboxylic esters are reduced to alcohols by catalytic hydrogenation in presence of copper chromate as catalyst under high temperature and pressure. Physical properties of alcohols. Physical state. At ordinary temperature, lower alcohols are colorless liquids with distinct smell and burning taste. The higher members are colorless, odorless, waxy solids. Hydrogen bonding. Since alcohols contain a hydrogen attached to the strongly electronegative oxygen atom. Therefore, extensive intermolecular H bonding occurs among alcohol molecules. As a result, alcohols exist as associated molecules rather than discrete monomeric molecules as shown below. Some important consequences of H bonding are discussed below. Boiling points. The boiling points of alcohols are much higher than hydrocarbons, alkyl halides, and ethers of comparable molecular masses. For example, ethyl alcohol, propane, methyl chloride, dimethyl ether. The high boiling point of alcohols can be easily explained on the basis of intermolecular H bonding existing between their molecules. Quite a large amount of energy is needed to break these extensive hydrogen bonds which hold a large number of alcohol molecules together. As a result, their boiling points are much higher than hydrocarbons. Ethers are alkyl halides of comparable molecular masses which do not form H bonds. Amongst isomeric alcohols, the boiling point decreases with branching due to corresponding decrease in surface area. Boiling points decrease in the order primary, secondary, tertiary. However, with increase in molecular mass, boiling point shows a regular increase. Solubility. The lower alcohols are highly soluble in water, but the solubility decreases with the increase in molecular mass of the alcohol. The solubility of alcohols in water which is due to the formation of hydrogen bonds between alcohol and water molecules. The extent of solubility of any alcohol in water depends upon the capability of the molecules' hydrogen bonds with water. As the molecular mass increases, the hydrocarbon part, alkyl group, because larger, which resists the formation of hydrogen bonds with water molecules and hence the stability decreasing. In other words, the solubility of alcohols in water decreases with lengthening of carbon Example, the solubility of the N-alcohol decreases as the length of the carbon chain increases. Amongst isomeric alcohols, the solubility increases with branching. This is due to the reason that branching increases the surface area of the non-polar hydrocarbon part decreases and hence the solubility increases. For examples, alcohol and butyl alcohol, isobutyl alcohol, sec-butyl alcohol, tersh-butyl alcohol. Chemical reactions of alcohols. The hydroxyl group is the functional group of alcohols. Therefore, most of the characteristic reactions, alcohols are the reactions of OH group. In general, the chemical reactions of alcohols can be divided into the following three categories. Reactions involving the cleavage of COH bond, ROH bond. Reactions involving the cleavage of COH bond, ROH. Reaction involving both the alkyl and the hydroxyl group of the alcohol molecule, that reaction of the alcohol molecule as a whole. Reaction involving the cleavage of OH bond. The ease of cleavage of OH bond of alcohols follows the sequence primary alcohol, secondary alcohol, tertiary alcohol. Some typical reactions of alcohols involving the cleavage of the OH bond are discussed below. Reaction with active metals, acidic nature. Alcohol react with active metals like sodium, potassium, magnesium and aluminium to form the corresponding metal oxides with the evolution of hydrogen gas. Methanol, sodium methoxide, ethanol, magnesium methoxide, tersh-butyl alcohol, aluminium tersh butoxide. This reaction suggests that alcohol are acidic in nature. The acidic character of alcohol is due to the reason that in alcohols hydrogen is attached to the highly electronegative oxygen atom, which withdraws the electrons of the OH bond towards itself. As a result, OH bond becomes weak and ultimately splits proton. In other words, the acidic character of alcohols is due to the ability of the oxygen atom to accommodate the negative charge. However, alcohols are weak acid, even weaker than water, as it's evident from the following reaction. Stronger acid, weaker acid. Here stronger acid H2O displaces a weaker acid ROH from its salt alkoxides reaction. This is due to the reason that the electron releasing inductive effect of the alkyl group increases the electron density around the oxygen atom. As a result, the electrons of the OH bond are not sufficiently attracted towards the oxygen atom and hence the release of a proton becomes difficult. In nutshell, we can say that the electron releasing inductive effect of the alkyl group makes the alcohols weaker acids than water. Comparison of acidic character of primary, secondary and tertiary alcohols. As we move from primary through secondary to tertiary alcohol, the number of alkyl groups attached to the carbon having the OH group increases from 1 to 2 to 3. As a result, the electron releasing inductive effect would be maximum in tertiary alcohols and minimum in primary alcohols. In other words, primary alcohols are the strongest acids and tertiary the weakest. Thus, the acidic strength of alcohols follow the order: primary, secondary, tertiary. Primary alcohol, secondary alcohol, tertiary alcohol. Obviously, the basic strength of the alkoxides follows the reverse order. In presence of strong acids, alcohols also act as Bronsted bases. This is due to the reason that the presence of lone pairs of electrons on the oxygen atom makes alcohols protons acceptors. Reaction with Grignard reagent. Alcohols being acidic react with Grignard reagents which act as a strong basis to form alkanes. It may however be noted here that the alkane formed corresponds to the alkyl group of the Grignard reagent. For example, alcohol, alkyl magnesium halide to form alkane. Ethanol, methyl magnesium iodide to methane, ethoxy magnesium iodide. Methanol, ethyl magnesium bromide, ethane, methoxy magnesium bromide. The H atoms attached to O, N and S are called active hydrogens. Compounds, alcohols, phenols, amines, thioalcohols, terminal alkynes containing active hydrogen on treatment with a Grignard reagent, usually CH3MgI, give quantitative yield of the hydrocarbon corresponding to the alkyl group of the Grignard reagent. Example, methane. Alcohol, 1-amine, primary amine, alkyne. This process is called Girver-Thionov's active hydrogen determination. Knowing the volume of methane involved as NTP, the number of active hydrogen atoms present in a compound can be determined. Thus, Girver-Thionov's procedure is useful for determining the number of active hydrogen atoms in an organic compound. Reaction with carboxylic acids. Alcohols react with carboxylic acid in presence of a few drops of concentrated H2SO4 or dry HCl gas as catalyst to form esters. For example, acid plus alcohol ester. Ethanoic acid plus ethanol, ethyl ethonate. This reaction, which is slow and reversible, is called esterification. When HCl gas is used as a catalyst, the reaction is usually referred as a Fischer-Spicer esterification. The mechanism of esterification involves the initial protonation of the carbonyl oxygen by the mineral acid to form the protonated carboxylic acid. As a result of protonation, the carbonyl carbon becomes more electropositive or electron deficient and hence readily undergoes nucleophilic attack by the lone pair of electrons on the oxygen atom of the alcohol to form the tetrahedral intermediate. This intermediate then undergoes proton transfer to form another tetrahedral intermediate. The intermediate subsequently loses a molecule of a water and a proton to give the ester as shown below. Isotopic tracer studies have confirmed that esterification involves cleavage of the OH bond of alcohols and COH bond of acids as suggested by the above mechanism. For example, when ordinary benzoic and is esterified with CH3-18OH, the ester methyl benzoate thus formed was found to be enriched in 18O, while the water formed contained only the ordinary oxygen. Relative reactivities of carboxylic acids and alcohols. The formation of tetrahedral intermediate during esterification is confirmed by the observation that the rate of esterification is sensitive to steric hindrance. As the number and the size of the substituents around the COOH group or the OH group in alcohols increases, the rate of esterification slows down. Thus, the order of reactivity follows the sequence. Acids and alcohols. Reactions with acid chlorides and anhydrides. When alcohols are treated with acid chlorides or anhydrides, the H atom of the OH group is replaced by the acyl RCO group to form esters. This reaction is called acylation. If the acid halide and anhydride used are acetyl chloride and acetic anhydride respectively, the reaction is usually termed as acetylation. However, if benzoyl chloride is used, the reaction is called benzoylation. Acetylation of alcohol is usually carried out in presence of a base such as pyridine or dimethyl aniline. Thus, acetyl chloride, ethyl alcohol, ethyl acetate, acetic anhydride, ethyl acetate, acetic acid. Benzoylation of alcohols is usually carried out in presence of aqueous NaOH, since benzoyl chloride is not readily hydrolyzed by alkalis. Thus, benzoyl chloride plus ethyl alcohol, ethyl benzoate, p-nitrobenzyl and 3,5-dinitrobenzoyl derivatives of the alcohols are usually well-defined crystalline solids and hence are used to characterize alcohols. The reaction of alcohols with benzoyl chloride and its derivative in presence of aqueous NaOH is called Shortman-Bowman reaction. Mechanism. The acylation of alcohols occurs by the following mechanism. With acid chlorides, you can see this. With acid anhydrides, you can see this. Reaction involving the cleavage of COH bond. Alcohols undergo a number of reactions involving the cleavage of COH bond. In these reactions, the order of reactivity of alcohols follows the sequence tertiary, secondary, primary. Some typical reactions of alcohols involving the cleavage of carbon-oxygen bond are discussed below. Reaction with halogen acids. Alcohols react with halogen acids to form haloalkanes, alkyl halides, and water. The order of reactivity of the halogen acids is HI, HBr, HCl. This is due to the reason that I ion is a better nucleophile than bromine ion, which in turn is better than Cl ion. The order of reactivity of alcohols in these reactions is tertiary, secondary, primary. This order of reactivity can be easily explained on the basis of plus I effect of the alkyl groups, which tend to stabilize the incipient carbocation or the carbocation intermediate. Since the stability of the carbocations decreases in the order tertiary, secondary, primary, therefore the order of reactivity of alcohols also decreases in the same order tertiary, secondary, primary. With HCl, due to low reactivity, the reactions of primary and secondary alcohols with HCl require the use of some Lewis acid catalyst such as anhydrous zinc chloride. However, no such catalyst is needed in the reactions of HCl with tertiary alcohols. ethanol, chloroethane, 2-propanol, 2-chloropropane, 2-methyl, 2-propanol, 2-chloro, 2-methylpropane. This reaction of primary and secondary alcohols with HCl in presence of anhydride ZnCl2 is called Grove's process with HBr. In this reaction, also a small amount of concentrated H2SO4 is added as a catalyst. No catalyst is required for secondary and tertiary alcohols which readily undergo dehydration in presence of concentrated H2SO4 to give alkenes. Ethanol to bromoethane. With HI, alkyl iodides are formed. Methanol to iodomethane. However, when an alcohol is heated with HI in presence of red phosphorus, hydrocarbon is produced. For example, methanol to methane. Mechanism. Primary alcohols react with halogen acids by SN2 mechanism, while secondary and tertiary alcohols tend to react by SN1 mechanism. SN2 mechanism. Primary alcohol, protonated primary alcohol. Role of anhydrous ZnCl2 in Grove's process. Anhydrous ZnCl2 being a Lewis acid accepts an electron pair from the oxygen atom of alcohols. The presence of positive charge on the oxygen atom weakens the RO bond which ultimately breaks to form a carbocation as shown in the SN1 mechanism discussed above. If the structure of R is such that it can undergo rearrangement to form a more stable carbocation, then the major product will be alkyl halide derived from the rearranged carbocation as discussed below. If, however, the concentration of zinc chloride is low, the reactivity occurs by SN2 mechanism. Rearrangement during SN1 reaction. The reaction of two secondary and tertiary alcohols with halogen acids occurs by SN1 mechanism and quite often gives rearranged products. For example, neopentyl alcohol on treatment with concentrated HCl yields 2-chloro 2-methylbutane instead of the expected neopentyl chloride. Reaction with phosphorus halide. Phosphorus halides such as PCl5, PCl3, PBr3, P plus Br2, Pi3, P plus I2 react with alcohols to form the corresponding haloalkenes or alkyl halides. Alcohol से alkyl chloride, phosphorus, oxychloride, alcohol, phosphorus acid, ethanol to chloroethane plus phosphorus oxychloride. Methanol to bromomethane plus phosphorus acid. Mechanism. The reaction between an alcohol and phosphorus trihalide PX3 say PCl3 occurs by the following mechanism. It involves the nucleophilic attack by the alcohol molecule on PCl3 when protonated alkyl dichlorophosphate is formed, which subsequently undergoes nucleophilic attack by the Cl negative ion forming the alkyl halide and HOPCl2. HOPCl2 then reacts with another molecule of ROH according to steps primary and secondary to form RCl and HO2PCl. Further reaction between HO2PCl and alcohols according to steps ultimately leads to the formation of 3 moles of alkyl halides and 1 mole of H3PO3 from 3 moles of alcohol and 1 mole of PCl3. The reaction between an alcohol and PCl5 occurs by a similar mechanism as shown below. Reaction with thionyl chloride. Alcohols react with thionyl chloride preferably in presence of a tertiary amine such as triethylamine or pyridine to form alkyl chlorides. Alcohol plus thionyl chloride say alkyl chloride, ethyl alcohol to ethyl chloride. This reaction is called Darzon's procedure. Since SO2 and HCl, both being gases, escape into the atmosphere leaving behind almost pure alkyl halide, therefore SOCl2 method is preferred over phosphorus halide method for the conversion of alcohols into alkyl chlorides. Mechanism. The nucleophilic attack of the alcohol molecule in thionyl chloride gives an adduct which subsequently loses a proton and a chloride ion to form alkyl chlorosulfide. This then undergoes another nucleophilic attack by the chloride ion forming an alkyl chloride SO2 and chloride ion. Role of base. Pyridine catalyzes this reaction in the following two ways. It neutralizes HCl produced in the first step, favoring the formation of alkyl chlorosulfite. It helps to pull out Cl negative ion, form alkyl chlorosulfite, thus formed, thereby favoring the formation of products. Reaction involving both alkyl and hydroxyl groups. Dehydration of alcohols. By dehydration, we mean removal of a molecule of water. Alcohols can dehydration gives alkenes. The dehydration is carried out by heating a suitable alcohol with protonic acid such as concentrated H2SO4 or H3PO4, Lewis acid such as anhydrous zinc chloride or alumina can also be used. Alcohol alkene. The actual temperature and the strength of the acid, however, depends upon the nature of alcohol used. For example, primary alcohol such as ethyl alcohol and propyl alcohol, etc., undergo dehydration when heated with 95% H2SO4 at 443 to 453 Kelvin to give ethylene and propylene respectively. Ethyl alcohol, ethylene, and propyl alcohol, primary alcohol to propylene. On the other hand, dehydration of secondary and tertiary alcohols occur with dilute H2SO4 and at lower temperatures. For example, isopropyl alcohol, propylene, tersh-butyl alcohol, isobutylene. Thus, the order of dehydration of alcohols follows the sequences tertiary, secondary, primary. In industry, the dehydration of alcohols is carried out by passing the vapors of an alcohol over heated alumina at 623 to 633 Kelvin. Ethyl alcohol, ethylene. Reactions of alcohols with concentrated H2SO4 under different conditions. The reaction between alcohols and concentrated H2SO4 is sensitive to conditions of the reaction, giving different products under different conditions. For example, ethyl alcohols react with concentrated H2SO4 at 383 Kelvin to form ethyl hydrogen sulfate. Ethyl alcohol to ethyl hydrogen sulfate. Ethyl hydrogen sulfate thus formed gives different products under different conditions. On distillation under reduced pressure, it gives diethyl sulfate. When heated with excess of ethyl alcohol at 413 Kelvin, it gives diethyl ether. When heated with excess of H2SO4 at 433 to 443 Kelvin, it gives ethylene. Mechanism. Dehydration of alcohols is an example of even reaction. It is believed to occur by the following three steps. Step 1. An alcohol being a Lewis base accepts a proton from H2SO4 to form oxynum salt, ethanol, protonated alcohol, oxynum salt. The presence of a positive charge on the highly electronegative oxygen atom weakens the CO bond. As a result, the protonated ethanol readily eliminates a molecule of H2O to form ethyl carbocation. This step is slow and hence is the rate determining step of the reaction. It may be noted here the dissociation of oxynum salt requires energy which is supplied by the energy released during solvation of carbocation by ion dipole interaction. Step 3. The carbocation formed in step 2 can either undergo nucleophilic attack by the bisulfate ion or may eliminate a proton since HSO4 is a very weak nucleophile. Therefore, nucleophile substitution reaction does not occur. Instead, elimination of a proton occurs to form ethylene. The whole process is reversible in order to shift the equilibrium towards right. Strong acids and high temperatures are used when the resulting alkene, being more volatile than the starting alcohol, escapes from the reaction mixture. Evidence in support of above mechanism. The following points support the above mechanism. Relative case of dehydration of alcohols. Step 2. In the above mechanism involving the formation of carbocation is the rate determining step of the reaction. Evidently, greater the stability of the carbocation, the more easily it would be formed and hence more readily that alcohol would dehydrate. Now, since the order of stability of carbocations follows the sequence tertiary, secondary, primary, hence the ease of dehydration also follows the same sequence. Tertiary alcohol, secondary alcohol, primary alcohol. Rearrangement of carbocation. Formation of unexpected products. It has been observed that certain alcohols on dehydration produce such alkenes in predominant amounts in which the position of the double bond is not that expected from the structure of the original alcohol. For example, The formation of such unexpected products can be easily explained in terms of the carbocation mechanism discussed above. We know that carbocations always tend to rearrange to more stable carbocations if the structure permits either by 1,2 hydric or 1,2 alkyl shift. Thus, in the dehydration of alcohols, if the initially formed carbocation is primary or secondary, and if the structure permits, it would always tend to rearrange to the more stable secondary or tertiary carbocation before losing a proton. For example, in the above reaction, the initially formed carbocation is N-butyl carbocation, which being primary undergoes a 1,2 hydride shift to form more stable sec-butyl carbocation before losing a proton. Thus, however, during dehydration of 3-methyl 2-butanol, the initially formed carbocation is secondary. It rearranges to the more stable tertiary carbocation by 1,2 hydride shift, which subsequently loses a proton to afford 2-methyl 2-butane as the major product. Thus, orientation of the dehydration. We have discussed above the dehydration of alcohols occurs through a carbocation intermediate. If the carbocation intermediate is such that it can eliminate a proton from either side, a mixture of alkene is obtained. In general, the alkene, which is more highly substituted, having lesser number of H atoms on the doubly bonded carbon atoms, is the major product of dehydration of alcohols. This generalization is called Sazov's rule. The formation of these products can be readily explained in terms of the rearrangement of the initially formed less stable carbocation to the more stable carbocation followed by loss of a proton as shown above. Further, if the major product is also capable of showing cis-trans isomerism, then it is always the thermodynamically more stable trans product which predominates. For example, dehydration of 2-butanol gives 70% of trans 2-butane, 10% of cis 2-butene, and about 20% of 1-butene. Oxidation of alcohols involves the formation of carbon oxygen double bond with cleavage of OH and COH bonds. These are also called dehydrogenation reactions since these involve loss of hydrogen from the alcohol molecule. The oxidation of alcohols can be carried out with a variety of reagents such as neutral acidic or alkaline KMNO4, acidified K2Cr2O7 or diluted HNO3. The ease of oxidation and nature of the products, however, depending upon the type of alcohols used. Primary alcohols are easily oxidized first to aldehydes and then to acids, both containing the same number of carbon atoms as the original alcohol. CRBI reagents such as Collins reagent, chromium trioxide pyridine complex, and Corey's reagent. Pyridinium chlorochromate in anhydrous medium are used as the oxidizing agents for the isolation of aldehydes. Secondary alcohols are easily oxidized to ketones with the same number of carbon atoms. However, ketones resist further oxidation, but under drastic conditions they are oxidized to carboxylic acids containing lesser numbers of carbon atoms than the original alcohol. Isopropyl alcohol, acetone, acetic acid. This oxidation can be stopped at the ketone stage by using chromic anhydride CrO3. Tertiary alcohols are resistant to oxidation in neutral or alkaline KMNO4 solution but are readily oxidized by acid oxidizing agents K2Cr2O7 H2SO4 or KMNO4 H2SO4 to a mixture of a ketone and an acid each containing lesser number of carbon atoms than the original alcohol. The oxidation presumably occurs with alkenes formed through dehydration of alcohols under acidic condition, for example, tertiary butyl alcohol to methyl prop1ene to acetone, 2-methyl butan to ol 2 methyl but to ene acetone plus acetic acid. Action of hot copper. Different classes of alcohols give different products when their vapors are passed over heated copper at 573 Kelvin. Primary alcohols undergo dehydrogenation to give aldehyde. Secondary alcohols also undergoes dehydrogenation to keep ketones. Tertiary alcohols, however, undergo dehydration to form alkenes. 2-methyl propan-2-ol, 2-methylpropan, 1-ene. Distinction between primary, secondary, and tertiary alcohols. The three classes of alcohols can be distinguished from one another by the following tests. Oxidation. The three types of alcohols yield different products on oxidation are explained on pages 121 to 122. By identifying the products of oxidation, it is possible to distinguish between the three types of alcohols. Action of hot copper. When vapors of alcohols are passed over hot copper at 573 Kelvin, primary and secondary alcohols undergo dehydrogenation to give aldehydes and ketones respectively, while tertiary alcohols undergo dehydration to give alkenes as explained on pages 122 to 123. Victor Meier's test. This test consists of the following steps. The given alcohol is first converted into its alkyl iodide by treating it with phosphorus and iodine Pi2. The alkyl iodide is then treated with silver nitride AgNO2 to convert it into its corresponding nitroalkane. The nitroalkane is then treated with nitrous acid HNO2, that is NaNO2 plus 2HCl. The resulting solution is finally made alkaline with aqueous NaOH or KOH. If blood red coloration appears, it indicates a primary alcohol. If blue coloration appears, it indicates a secondary alcohol. If the solution remains colorless, it indicates a tertiary alcohol. Lucas test. This test is based upon the difference in reactivity of primary, secondary, and tertiary alcohols with hydrochloric acid. This test consists of treating an alcohol with Lucas reagent and equimolar. Mixture of concentrated HCl and anhydrous ZnCl2 at room temperature when turbidity due to the formation of unsoluble alkyl chlorides is observed. If the turbidity appears immediately, the alcohol is tertiary. If the turbidity appears in about 5 minutes, the alcohol is secondary. A primary alcohol, however, does not react with Lucas reagent at room temperature and hence no turbidity is formed. Primary alcohol, no reaction, and hence no turbidity at room temperature. Secondary alcohol, turbidity appears in about 5 minutes. Tertiary alcohol, turbidity appears immediately. Interconversions of primary, secondary, and tertiary alcohols. Using a proper choice of reactions, if it possible, to convert one class of alcohols to the other. Conversion of primary alcohols to secondary alcohols and vice versa. N-propyl alcohol to isopropyl alcohol, isopropyl alcohol to N-propyl alcohol, ethyl alcohol to sec-butyl alcohol, sec-butyl alcohol to ethyl alcohol. Conversion of primary alcohols to tertiary alcohols and vice versa. Isobutyl alcohols to tertiary alcohol, tertiary alcohol to isobutyl alcohol. Conversion of secondary alcohols to tertiary alcohols and vice versa. 3-methyl 2-butanol to 2-methyl 2-butanol. 3-methyl 2-butanol 2-methyl 2-butanol to 3-methyl 2-butanol. Dihydric alcohols. Compounds containing two hydroxyl groups attached to different carbon atoms of their molecules are called dihydric alcohols. The general formula of dihydric alcohols is CH2NOH2, where N is equal to 2, 3, 4, etc. Because of their sweet taste, they are commonly called glycols. Depending upon the relative position of the two hydroxyl groups, these are classified as alpha, beta, gamma glycols, etc. Thus, alpha glycol is 1,2 glycol, beta glycol is 1,3 glycol. Glycol is one in which the two OH groups are attached to the terminal carbon atom. Alpha glycols are also called vicinal glycols. Dihydric alcohols are named by the following two steps. Common system. In this system, alpha glycols are called Vic glycols are named by the adding the word glycol to the name of the alkene from which they can be prepared by direct hydroxylation. For example, ethylene glycol, propylene glycol are named as the corresponding polymethylene glycols. For example, trimethylene glycol, pentamethylene glycol. IUPAC system. In this system, dihydric alcohols are named as diols. Their individual names are obtained by adding the word diol to the name of the corresponding alkane. Thus, their class name is alkane diol. The position of two hydroxyl groups is, however, indicated by Arabic numerals. For example, ethane 1,2 diol, propane 1,2 diol, propan 1,3 diol. Methods of formation of vicinal glycols. Vicinal glycols or 1,2 glycols are generally prepared by the following methods. By hydroxylation of alkenes. Vicinal glycols can be conventionally prepared by hydroxylation of alkenes either by treatment with a cold dilute 1% aqueous alkaline solution of potassium permanganate Bayer's reagent or by treatment with ozonium tetroxide followed by hydrolysis with an aqueous solution of Na2SO3 or NaHSO3. In both the cases, the reaction occurs through intermediate formation of a cyclic ester which upon subsequent hydrolysis gives vicinal glycols. The Mn compound formed as a result of hydrolysis undergoes disproportion to MnO2 and permanganate ion. Similarly, with OSO4 cyclic osmate ester is produced. Stereochemistry. Since in both these reactions a cyclic ester is formed as an intermediate, therefore both these reactions are syn hydroxylation processes. The two hydroxyl groups are added from the same side of the double bond to afford cis-1,2 glycols. For example, cyclohexene cis-1,2 cyclohexene diol. By hydrolysis of epoxides, acid or base catalyst hydrolysis of epoxides are also called oxiranes gives vicinal glycols. For example, ethylene epoxide, ethylene glycol. In case of cyclic oxiranes, ring opening occurs by SN2 mechanism to afford trans 1,2 diols. For example, 1,2 epoxy cyclohexane trans 1,2 cyclohexane diol. The epoxides needed for the purpose are prepared by the action of para-acids such as perbenzoic acid, M-chloroperbenzoic acid, performic acid, etc. or alkenes. For example, ethylene plus perbenzoic acid to ethylene epoxide plus benzoic acid. Hydrolysis of vicinal dialkenes. Vicinal glycols can also be prepared by hydrolysis of vicinal dihaloalkenes by aqueous Na2CO3 solution. Bimolecular reduction of carbonyl compounds. Ketones on reduction with magnesium in an inert solvent such as benzene, ether, etc. or magnesium amalgam and water give pinacols. For example, acetone 2,2,3-dimethyl butane 2,3-diol. It means pinacol. This reduction may also be carried out photochemically. For example, benzophenone plus isopropyl alcohol to benzapinacol acetone. Mechanism. The bimolecular reduction of ketones with magnesium amalgam is believed to occur free radical mechanism as depicted below. Reaction of 1,2 diketones with Grignard reagents. This method is generally used for the preparation of higher vicinal diols. For example, butane 2,3-dione 1,2 glycol. Physical properties. State, odor, color, etc. Ethane 1,2 diol is a colorless viscous liquid with sweet taste. Viscosity. Because of the presence of two OH group in its molecule, ethane 1,2 diol undergoes extensive intermolecular hydrogen bonding. As a result, ethane 1,2 diol molecules are highly associative and thus it has a high viscosity. Solubility. Because of the presence of two OH group, ethane 1,2 diol forms hydrogen bonds with water. As a result, ethane 1,2 diol is highly soluble in water. Further, being a polar compound, it is so insoluble in non-polar and weakly polar solvents such as chloroform, ether, etc. Boiling point. Due to extensive intermolecular hydrogen bonding, the boiling point of ethane 1,2 diol is quite high, 470 Kelvin. Chemical reactions. The molecule of ethylene glycol contains two primary alcoholic groups, thus its chemical reactions are essentially those of primary alcohols Some important chemical reactions of vicinal glycols are discussed below. Reaction with acid active metals. Vicinal glycols react with active metals like Na forming mono and disodium salt with the liberation of H2 gas. Ethylene glycol, monosodium glycolate, disodium glycolate. It may be noted that the two hydroxyl groups react one after the other. When one OH group has completely reacted, the second starts reacting rather slowly. This is due to the reason that in glycol molecule, the I effect of one OH group makes the other more acidic, which reacts with the metal rapidly. However, when one OH group has completely reacted, the alkoxide formed CH2O exerts plus I effect, which makes the other OH group less acidic, and thus the second OH group reacts slowly, and it is because of this reason that the second OH group needs more vigorous conditions for the reaction to occur. Reaction with hydrogen halides. Vicinal glycols react with hydrogen halides in two stages to form dihaloalkanes, for example with HCl. Ethylene glycol reacts first gives ethylene chlorohydrin and then ethylene dichloride. Ethylene glycol to ethylene chlorohydrin, ethylene dichloride. Here again the displacement of second OH group is more difficult than the first. This may be explained as follows. The reaction occurs with initial protonation of the OH group to form the oxonium salt, which is subsequently displaced by nucleophilic attack by the chloride ion either by SN1 or SN2 reaction. Once one OH group has been replaced by Cl, the Cl atom thus introduced exerts its I effect. As a result, electron density on the oxygen atom of the other OH group decreases. This makes the protonation of second OH group rather difficult, and that is why higher temperature is needed to replace the second OH group by Cl atom. Similarly, with HBr, first bromohydrin and then ethylene dibromide is formed. However, with Hi only, ethylene is produced. Ethylene glycol to ethylene diiodide, unstable ethylene. Reaction with phosphorus pentachloride or thionyl chloride. Ethylene glycol reacts with PCl5 or thionyl chloride to form ethylene dichloride. Ethylene glycol to ethylene dichloride. Ethylene glycol to ethylene dichloride. Reaction with phosphorus trihalides. When reacted with PCl3 or PBr3, vicinal glycols give the corresponding dichlorides or dibromides. However, with Pi3, Pi plus I2, the diiodide first formed being unstable decomposes to form an alkene and I2, for example. Reaction with nitric acid. With a mixture of concentrated HNO3 plus concentrated H2SO4, ethylene dinitrite is formed. Reaction with monocarboxylic acids. On treatment with monocarboxylic acids, ethylene glycols form mono or diesters depending on the relative amount of the reactants. For example, glycol diacetate is obtained when glycol is heated with glacial acetic acid in presence of a small amount of concentrated H2SO4 as a catalyst. Reaction with dicarboxylic acid. When ethylene glycol is heated with dicarboxylic acid or esters, condensation polymers called polyesters are obtained. For example, condensation of ethylene glycol with 3-pentylic acid or its methyl ester gives terylene or dacron. Reaction with aldehydes and ketones. When heated with aldehydes and ketones in presence of P toluene sulfonic acid PTS as catalyst, ethylene glycol gives cyclic acetyls and cyclic ketones 1,3-dioxylanes respectively. These acetyls and ketones are widely used for protecting a carbonyl group in polyfunctional compounds where the reactions are desired at the other functional group in basic medium. After the desired reaction, the carbonyl group is regenerated by hydrolysis of the acetyl or the ketyl with dilute mineral acids HCl or H2SO4. Dehydration. Action of heat. Ethylene glycol when heated to 773 Kelvin gives ethylene oxide. With anhydrous zinc chloride, ethylene glycol gives acetaldehyde. With concentrated H2SO4, when distilled with concentrated H2SO4, ethylene glycol gives 1,4-dioxane, which is used as an industrial solvent. With concentrated H3PO4, when heated with concentrated H3PO4, ethylene glycol gives diethylene glycol, which is widely used as an industrial solvent. Oxidation. Oxidation of glycols gives a variety of different products depending upon the conditions of the reaction and the type of reagent used. In case of 1,2-glycols, products may arise with or without the fission of carbon-carbon bond. Oxidation, in which the carbon-carbon bond remains intact. Oxidation of 1,2-glycols with usual oxidizing agents such as HNO3 gives a variety of products in which both the alcoholic groups are oxidized but the carbon-carbon bond remains intact. For example, ethylene glycol on oxidation with concentrated HNO3 mainly gives glycolic acid and oxalic acid. The other oxidation products such as glycoxylic acid are also formed in small quantities because they are more readily oxidized than glycol itself. Oxidation involving fission of carbon-carbon bond holding the hydroxyl groups. 1,2-glycols on oxidation with an aqueous solution of periodic acid HiO4 or lead tetraacetate PbOCOCH3 4 in an organic solvent undergo fission of the carbon-carbon bond holding the OH group, leading to the formation of aldehydes, ketones or both depending upon the structure of the glycol. The oxidation of 1,2-glycols with periodic acid to give carbonyl compounds is also sometimes called as a Mel-Praed reaction. It may be noted that in both these oxidation reactions, for every C-C bond broken formed at each other, both these reagents are specific for 1,2-glycol splitting. They can oxidize 1,2-glycols but not 1,2 or higher glycols. For example, propane 1,2-diol, acetaldehyde, formaldehyde, propane 1,3-diol. Besides 1,2-glycols, HiO4 can also bring about the oxidative cleavage of 1,2-dialdehydes, 1,2-diketones, alpha-hydroxyaldehydes, alpha-hydroxyketones, but not of alpha-hydroxy acids, alpha-hydroxy esters, alpha-hydroxy esters, alpha-hydroxy acetals, ethers. Thus, mechanism. Oxidation with periodic acid. In aqueous solution, periodic acid undergoes hydration to form H5IO6, which ionizes to form the active species H4IO6. The active species first reacts with 1,2-glycol to form the 5-membered cyclic ester, which loses a molecule of H2O to form another 5-membered cyclic intermediate. The intermediate in turn undergoes simultaneous oxidation reduction process with the cleavage of carbon-carbon bond, forming the corresponding carbonyl compounds as depicted below. Oxidation with lead tetraacetate. Similarly, lead tetraacetate first reacts with 1,2-glycol to form a 5-membered cyclic ester intermediate, which subsequently decomposes to form the corresponding carbonyl compounds. Use of Mel-Praed reaction. The oxidation of 1,2-glycols with HiO4 takes place in quantitative yield by determining the quantity of HiO4 and used and the nature and amounts of products formed. It is possible to determine the structure of polyhydroxy compounds, particularly carbohydrates, which are polyhydroxyaldehydes or ketones, as discussed below. Structure determination. Let us consider the oxidative cleavage of 3 isomeric butanediols: 1,2-butanediol, 2,3-butanediol, and 1,3-butanediol by HiO4. 1,2-butanediol reacts with 1 mole of HiO4 to give an equimolar mixture of formaldehyde and propionaldehyde. 2,3-butanediol also reacts with 1 mole of HiO4 but gives 2 moles of acetaldehyde only. In contrast, 1,3-butanediol does not react with HiO4 because it does not have OH groups attached to adjacent carbon atoms. Thus, by identifying the nature of the product, it is impossible to determine the structure of the given diol. Determination of number of OH groups present on adjacent carbon atoms in polyhydroxy compounds. In case of simple polyhydroxy compounds, for every 2 adjacent hydroxyl groups, 1 mole of HiO4 is used. Therefore, if there are n adjacent hydroxyl groups, moles of HiO4 would be used. Thus, by knowing the number of moles of HiO4 used, the number of adjacent hydroxyl groups in a molecule can be determined. For example, oxidation of 1 mole of glycerol uses 2 moles of HiO4 per mole of glycerol. Therefore, it contains 3 OH groups. It may be noted here that internal OH groups are oxidized to formic acid during HiO4 oxidation. However, in case of polyhydroxyaldehydes or ketones, since oxidation of CHOH, CHO or COCH2OH moiety requires 1 mole of HiO4, therefore number of moles of HiO4 used in equal to number of adjacent OH groups present. For example, oxidation of 1 mole of glucose requires 5 moles of HiO4. Therefore, glucose has 5 adjacent hydroxyl groups. Similarly, oxidation of 1 mole of fructose also requires 5 moles of HiO4. Therefore, it also contains 5 OH groups. Pinacolane rearrangement. Substituted vicinal diols are referred to as pinacoles. Thus, when 2,3-dimethyl 2,3-butanediol, usually called pinacol, is heated with concentrated H2SO4, it undergoes dehydration and with molecular rearrangement to form tertiary butyl methyl ketone are called pinacoline. Other substituted vicinal diols are known to undergo similar acid catalyst rearrangements. All these rearrangements are collectively called pinacoline rearrangement. Mechanism. Pinacoline rearrangement is believed to undergo by the following steps. Step 1 involves protonation of pinacol in presence of a strong mineral acid such as H2SO4 to form protonated pinacol. Step 2 protonated pinacol loses a molecule of water to form a carbocation. In step 3 carbocation undergoes rearrangement by 1,2-methyl shift to form another carbocation. The driving force for this rearrangement is the greater stability of carbocation by resonance over carbocation. In step 4 the carbocation loses a proton to yield pinacoline as the final product. Kinetic measurement have shown that the conversion of the rate determining step of the reactions. Stereochemistry. This rearrangement is an intermolecular process. The migrating methyl group begins to attach itself to the positive carbon before separating from its original position as shown below. This is supposed by the observation that when the rearrangement of two different pinacoles is carried out together, only two rearrangements products are formed. The absence of crossover products conclusively proves that the migrating group of one pinacol never gets detached from the initial carbocation so that it may get attached to the carbocation produced from other pinacol. From the above discussion, it is evident that is pinacol rearrangement, the migrating group retains its original configuration. The new bond formed will have the same relative positions of atoms and groups around it as possessed by the old bond. In contrast, if the migrating group were to get completely detached before attaching itself to electron deficient carbon, it would lead to race mission in case of chiral pinacols, but in actual practice race mission does not occur. Evidence in favor of carbocation intermediate. When the rearrangement of pinacol is carried out in presence of H2-18O and the reaction is stopped before completion, the recovered pinacol is found to contain the 18O isotope, suggesting reversible formation of carbocation. This establishes the pinacol-pinacoline rearrangement occurs through carbocation intermediate. In case of unsymmetrical substituted glycols out of the two OH group, that OH group departs when produces a more stable carbocation. For example, 1,1-diphenyl 2-methyl 1,2-propanediol on treatment, H2SO4 produces 3,3-dimethyl 2-butanol by methyl migration and not 2-methyl 1,2-diphenyl propane. Phenyl migration as shown below. 1,1-diphenyl 2-methyl 1,2-propanediol more stable carbocation stabilized by resonance over pH groups. 3,3-diphenyl 2-butanol. Migratory aptitude of groups. In general, it has been observed that the migratory aptitude of an alkyl group is much greater than that of an alkyl group or hydrogen. Amongst aryl groups, migratory aptitude increases as the electron density in the aryl group increases. P-chlorophenyl, phenyl, P-toluol, P-methoxyphenyl for example. Trihydric alcohols. As the name suggests, trihydric alcohols are compound which contains 3 hydroxyl groups attached to 3 different carbon atoms in the IUPAC system. They are known as triols. For example, CH2OH, CHOH, CH2OH, propane 1,2,3 triol. In the common system, propane 1,2,3 triol is called glycerol, also popularly known as glycerin. Glycerol propane 1,2,3 triol. It is the simplest and the most important trihydrate alcohol. It occurs in almost all vegetable and animal oils and fats, which are the triesters of glycerol, with long chain fatty acids. In other words, oils and fats are triacyl glycerols and are commonly known as triglycerides. Oils and fats may be represented by the general formula. The triglycerides may be further classified as simple or mixed according to the three alkyl groups are identical or different. For example, glycerol tripylnitrite, glycerol beta plameto, glycerol. Methods of formation. Glycerol is usually prepared by the following methods. By saponification of oils and fats, glycerol is mainly obtained by the hydrolysis of oils and fats with caustic soda. Since sodium salts of fatty acids are called soaps, the above hydrolysis reaction is called saponification. In fact, this reaction is used for the manufacture of soap. Thus, glycerol is obtained as a byproduct from soap industry. From propylene. On a commercial scale, glycerol is also prepared from propylene. Propylene needed for the purpose is obtained by cracking of petroleum. The following reaction sequence is complete. It may be noted here that at high temperature, propylene reacts with chlorine to give a substitution rather than an addition product, propylene dichloride. The reaction being that under conditions of high temperature, the addition reaction is reversible. Propylene dichloride decomposes to give propylene back, but the substitution reaction is irreversible. Synthesis from its elements. Glycerol can be synthesized from its elements as follows. Now convert propylene to glycerol as discussed above. Physical properties. Glycerol is a colorless, viscous, odorless and hygroscopic liquid with sweetness. It boils at 563 Kelvin with some decomposition. It is miscible with water and alcohol in all proportions. However, it is insoluble in ether and chloroform. These properties can be explained as further. Viscosity. Because of the presence of 3 OH group, glycerol undergo extensive intermolecular H bonding. As a result, the glycerol molecules are highly associated and thus glycerol has a high viscosity, even higher than that of ethylene glycol, which has 2 OH groups per molecule. Solubility. Because of the presence of 3 OH groups, glycerol forms hydrogen bonds with water. As a result, like ethylene glycol, glycerol is also highly soluble in water. Further, being a polar compound, it is insoluble in non-polar and weakly polar solvents like carbon tetrachloride, chloroform, ether, etc. Boiling point. Due to extensive intermolecular hydrogen bonding, the boiling point of glycerol is quite high, 563 Kelvin, even higher than that of ethylene glycol, 470 Kelvin. Chemical reactions. Glycerol contains 1 secondary and 2 primary alcoholic groups and it undergoes reactions typical of both these groups. However, due to strong interaction between these 3 OH groups, it also undergoes some special reactions typical of polyhydric alcohol. Some of the important reactions of glycerol are discussed below. Reaction with sodium metal. Sodium readily reacts with one primary alcoholic group at room temperature and less readily with the second primary alcoholic group at 373 Kelvin with the evolution of H2 gas. The secondary alcoholic group is not attacked at all. Reaction with halogen acids. With hydrogen chloride, glycerol and dry HCl react at 383 Kelvin to form a mixture of alpha beta glycerol monochlorohydrins. However, on passing more of HCl gas 25% in excess at 383 Kelvin, glycerol gives a mixture of alpha dichlorohydrin and alpha beta dichlorohydrin. To replace the third hydroxyl groups in either of the 2 dichlorohydrins, PCl5 or PCl3 is used. With hydrogen bromide, like HCl, hydrogen bromide gives similar reactions. Look at this. With hydrogen iodide, different products are obtained under different conditions. When glycerol is treated with a small amount of HI or Pi3 alkyl iodide is formed. When a large amount of HI is used, the main product is isopropyl iodide, which is believed to be formed by the action of HI on alkyl iodide according to the following reactions. Reaction with concentrated nitric acid and sulfuric acid nitration. When glycerol is added to a mixture of concentrated H2SO4 and concentrated HNO3 at 283 to 298 Kelvin, glycerol trinitrate is formed, which commonly but incorrectly called as nitroglycerin. Glycerol trinitrate is a colorless oily liquid. It explodes violently on heating or detonation. Alfred, the scientist in whose name the Nobel Prizes have been instituted, found that nitroglycerin can be stabilized by observing on a kind of porous earth, a mixture of glycerol trinitrate and glycerol dinitrate. Absorbed on is called dynamite. However, these days dynamite is manufactured by using sawdust or wood pulp as the absorbent and adding solid ammonium nitrate. Reaction with KHSO4 dehydration when heated with anhydrous potassium hydrogen sulfate. Anhydrous with zinc chloride or concentrated H2SO4, glycerol undergoes dehydration to forms acrolein unsaturated aldehyde. Oxidation. Glycerol can form a large number of products on oxidation. The actual product obtained, however, depends upon the nature of the oxidizing agent used. With diluted HNO3, a mixture of glycerol acid and tartronic acid is produced. With concentrated HNO3, mainly glyceric acid is obtained. With bismuth nitrate, only mesoxalic acid is formed. Mild oxidizing agents like bromine water, sodium hypobromite, and Fenton's reagent give a mixture of glyceraldehyde and dihydroxyacetone. This mixture is called glycerol. With periodic HiO4 acid, with periodic acid, glycerol undergoes oxidative cleavage to form formaldehyde 2 moles and formic acid 1 mole. During this oxidation, periodic acid itself is reduced to iodic acid with acidified potassium permanganate. When heated with acidified KMnO4 solution, glycerol gets oxidized to oxalic acid, carbon dioxide, and water. Reaction with phosphorus halides. All the three OH groups of glycerol reacts when treated with PCl5 or PCl3 to form 1,2,3 dichloropropane. With PBr3, glycerol tribromide is formed, whereas Pi3 behaves exactly like Hi. With a small amount of Pi3, allyl iodide is obtained. However, with a large amount of Pi3, the main product is isopropyl iodide. Reaction with monocarboxylic acids. Glycerol reacts with monocarboxylic acid to form mono-D and triesters depending upon the amount of the acid used and the temperature of the reaction. An excess of the acid and high temperature favor the formation of triesters. For example, with acetic acid, glycerol monoacetate, diacetate, and triacetate may be formed. Acetylation. When treated with acetyl chloride, glycerol forms diglycerol triacetate. Reaction with oxalic acid. At 110 Celsius, 383 Kelvin, when oxalic acid is heated with glycerol at 383 Kelvin, it forms glycerol monooxalate, which loses a molecule of CO2 to give glycerol monoformate. The latter then undergoes hydrolysis to yield formic acid. At 230 Kelvin, 230 Celsius, 503 Kelvin, oxalic acid reacts with glycerol to form glycerol dioxalate, which loses 2 molecules of carbon dioxide to give allyl alcohol. Uses. In the preparation of nitroglycerin used in making dynamite, a mixture of glycerol trinitrate and glycerol dinitrate observed on a kind of porous earth is called dynamite. Dynamite was discovered by Alfred Nobel, in whose memory the Nobel Prizes have been instituted. Dynamite is not only used for making bombs but also for making tunnels by blasting of rocks. Nitroglycerin is also used for treatment of anemia pectoris. As an antifreeze in automobile radiators, it lowers the freezing point of water and thus does not allow it to freeze in cold weather. In medicines like cough serums, lotions, etc. In the production of glyptal or allied resin, a cross-linked polyester obtained by the condensation polymerization of glycerol and phthalic acid, which is used in the manufacture of paints and lacquers.